So here we go. So circuit analysis. So we're going to introduce first off a couple of terms, a couple of things to remember, a couple of definitions. This first one you already know, but I'm going to read through it and then we're going to talk about it a little bit. The potential difference between 2 points, A and Z, in a circuit is equal to the sum of the potential differences between any number of successive pairs of points between A and Z. And so this notation that I'm using to represent a potential difference uses V as the variable for potential, and we have two subscripts. Each subscript refers to a point in our circuit. So let's say we have a circuit and we'll start off with point A, and maybe this circuit consists of a number of resistors in series for simplicity. And we will start off at point A and end up at point Z. Resistors, when they have a current through them, have a certain amount of potential difference given to us by Ohm's law. Now, Ohm's law is a relationship for ohmic resistors, resistors such that the value of resistance does not change with potential difference, nor does it change with current. So Ohm's law is a relationship that looks like this. Delta V potential difference is equal to the product of current times resistance. Now, depending on the direction of current, we might say the potential difference is the positive product of current times resistance, or we'll say the potential difference is equal to the negative of the current times the resistance. We'll talk about when it's positive and when it's negative later. For now, let's just look at the magnitude of the potential difference between 2 points. So the potential difference between, let's say, points A and Z can be written like this. It's the potential at point Z minus the potential at point A. And the abbreviation is just written like this, the V sub AZ. And what this means is if we take any number of successive points in between A and Z, all we have to do is sum the potential differences between those individual points. So the potential difference from A to Z is equal to the potential difference from A to B plus the potential difference from B to C plus the potential difference from C to D plus, and you can add any number of points until you get to your final pair of points. Now, for this problem, if we just look at the magnitude of the potential differences between each of these points, we would have the potential difference from A to Z is equal to, let's say there is a current going through this circuit. And we will say the current is going to the left. I will call this current I. And we are going to add the potential difference by going to the right. So the path we're taking, in other words, we're going to add from A to Z, but the current is going opposite our path. You're going to learn shortly that whenever current is opposite the direction that you go to measure voltage through a resistor, then the potential difference across that resistor is going to be a positive IR. So with this said, going from A to Z, we would have the, let's label this resistor 1, resistor 2, resistor 3, and we'll just say this is resistor, I'll just call it resistor Z. So this would be the sum of the potential difference across resistor 1 plus the potential difference across resistor 2 plus the potential difference across resistor 3, all the way until we get to our last resistor. The moral of the story here is not just for resistors, but for any component. If you go from one point to another, the potential difference between those 2 points can be determined by summing up all of the potential differences between pairs of points that make up the segment you're looking at.